Hi everyone, my name's Alex and welcome to an Engineer's Findings. And to the more regular viewers of this channel, sorry for my absence. And no, I've not been captured by the lumber industry. It's just that the old coat was quite wasted and this new one was on quadruple sale. So forgive the colors, we have to deal with it. Anyway, story of today's video is I want to take you along reconditioning or restoring the slotting head attachment for the Mikron WF1 mill. Believe it or not, those slotting heads are quite rare. So even though the slotting head was quite expensive and I was also not very sure about the condition of the slotting head, I almost immediately had to buy it because firstly, as I said, those slotting heads are quite rare. I'm not sure if there were a lot of those built in the first place. And secondly, what are the chances these days to be able to buy a slotting head for this machine that is not part of a package deal where you have to buy another mill? So now you may argue, Alex, what do you need a slotting head attachment for anyways? This is obsolete and you might need this only every 10 years or so. Yeah, fair argument, but you know that entirely depends upon the nature of the parts that you make. And from the top of my head, when I think back how many parts I had to send out in the past to internal spline it by wire EDM cutting, and if I add up those bills for those parts, I could have bought this slotting head already, if it was available back then. And now, for example, I have to make a few of those crank levers, which are internally splined. They have a very small internal spline and a very fine one. So I'd rather make these in-house than send those out for wire EDM cutting. Also, not just because of the price for wire EDM cutting, but also because I'm quicker that way. So this is a benefit that I can use with the customers if I'm really quick with this kind of work. And since I can grind the tools myself on the D-bit grinder, I can do this no problem with a slotting head. Now, why am I talking about reconditioning this head? You can see on the dovetail slide that this head was used. However, you can also see it has not been abused. Abuse on the slotting heads is usually quite readily visible when you see the lower side of the ram and you see some chowdering, as Tom Lipton would call it, going on there. But there's none of that visible here. However, when I first installed the head on the machine and test fitted it, I could find that, forgive me, I already took out the drive gear from the slotting head before I made this video. So this drive gear is driven by the horizontal spindle of the machine. It sits in the back of the slotting head here. And the machine horizontal spindle interfaces with these drive dogs here and thereby turns the gear. So the one thing I found is I can only install the head with the gear in one position. I cannot turn it 180 degrees because then it won't install. So it seems this axle pin here is a little off center in relation to the horizontal spindle. And I suspect that this is because this axle pin was pressed in a little crooked by the original manufacturer. Believe it or not, that's my suspicion. And I suspect that because the hole on the inside of the housing has a little galling going on one side of the bore. So I assume this pin was pressed in a little crooked and then pulled back straight a little, but not perfectly as we like it. So I think we may be able to solve this problem by relapping the bore and relapping out the damage that is in the bore and then reinstalling this gear. And I'm not sure if you can see from that distance, but the gear teeth here, you can see the wear pattern, or it's not really wear, it's just visible where the gears have meshed. This one with the second gear, you can see it's only over a part of the gear tooth width. And why is that? And eventually I came up with the suspicion that the second gear that's on the inside of the slotting head is assembled the wrong way around. This must also have been a mistake by the original manufacturer, because I don't see a lot of evidence on the inside of the slotting head. We will see together when we disassemble this, but I could not see a lot of evidence that somebody has been in there already. So these two things are the important things we want to remedy. Then the tool holder pin here in the front is a little stuck, so it moves a little. You have to use a little force to move it, and that's not nice for installing the tool, so we will lap the bore of this one to give it a nice movement again. And let's see in this video how far my motivation takes me. It would also be nice to touch up the dovetail slide here a bit by scraping it. Something that also annoys me a bit, I almost forgot it, is I don't like this cover, because this cover also covers the oiling port for the ram. The oiling port that supplies the dovetail slide and the connecting rod pin. So the quite important oiling port. And the oiling port is only visible or accessible whenever the ram is in its lowest position. So you have to adjust the largest stroke to get the ram into the lowest position, and only then the oiling port is accessible. Unless you completely take off that cover. But, you know, in my opinion, this is a bad design choice. Alright, so let's see when we disassemble this head what else we find, and if we can solve these problems. And in case you're interested, join me, why not? So let's start off with a custom-made aluminum lap here and some 14 micron diamond lapping compound to take care of that slightly deformed clamping hole here, tool clamping hole, that is, and our favorite choice of lubricant. So that lap here tightens by means of that nut in the back, and that pulls a conical pin on the inside and thereby ever so slightly expands the lap. And it's very important here to use a universal joint on the power tool drive so as to not put in sideward forces in this process. And if this is done correctly to our feel, then we may end up with a surface that is only attacked where it was deformed and not lapped where the surface was okay. So that's a nice kind of repair. And that's the way we want it. Nice. So now is the time to tear it all down and give each and every part a very thorough inspection to see which spare parts we have to come up with, which repairs we have to do, and what else is problematic. Now the dovetail slides, they show that this head has been run and used, but not too badly. I've seen worse on the wear side, so that's okay. The ram also looks okay. A little bit of wear, but not too much. So this is the connecting rod and the adjustable stroke crank in the background here, which I'm turning. So this setting should be almost 0 stroke. Yeah, right. And I wonder how this thing comes apart. Maybe by taking off the swivel clamps. Nuts look okay, not too much abuse here. It's a good sign. But no, it doesn't come apart that way. Maybe in the largest stroke setting. Yeah, no. No. Alright, we have to take out the clamping bolts first. Through this hole in the back. And let's see if that helps. Yeah, nice. So this gives you a clear view of the adjustable stroke crank, the clamping bolt, and the connecting rod. Connecting rod has plain bearings on either end. And they look okay. Right. So this is how the drive works, and where we have this meshing problem that we will address later. But first let's take out the dovetail adjusters. Now these are design-wise not the ultimate optimum solution, but they work. Housing is okay. So now let's get that crank out. Therefore we have to press out that bearing, because I guess it's not just a slip fit. Yeah, the snap ring comes loose, but the bearing definitely not. It's pressed in. And I'm using the pin in the back here to push onto the shaft, and those 3 pieces in the front to push on the housing. Now that puts load on the bearing, which is not good and will probably damage the bearing, but I don't care because I will replace the bearing anyways. Put in a new one. It's a standard bearing, not too bad. Right, so that's the crankshaft with its drive gear. The secondary bearing in the back, it's a needle bearing, and this cover. The drive gear is held in place with another snap ring. Let's hope that comes out. Yeah. This one tends to fight. Alright, the gear should be a slip fit, I guess. Would make sense to have a press fit here. Yeah. That comes off, nice. So the gear looks good. This is how they were assembled, while this is the right way they should be assembled, in my opinion. Okay, let's take a look at the housing, if we see any damages here. But all in all, it looks fairly okay. This is the hole where some galling is going on, where I suspect the pin was press fit in a tilted fashion. Somebody has to clean up all the gunky grease and oil. And don't worry about the toothbrush, it's not in personal use anymore. But even if it was, I'm just cleaning teeth here, alright? So give me a break. But the brass brush also has to help a little bit. But the gear cleans up like brand new, I guess. Toothbrush for the win. It's what the dentists say, I guess. So next we have to press off that bearing from the crankshaft, and I'm using these 2 nuts as a pushing device. So these are on the bottom here, not visible. Yeah. And now let's push out the crankshaft. Nice, Alex. That's the way you do it. Now, the stroke adjuster has this retaining pin so that you do not over adjust it. And fortunately, this retaining pin is a not too bad press fit. So I push it back here, and now I can get off the T-nut. Chaos is taking the overhand on the workbench. So this is the T-nut, and you can see in the back it has this slot that interfaces with the retaining pin, the adjuster bolt, and the crankshaft. So this is the drive gear, and you can here see how the gears were meshing, so they were not meshing over the full width. Here's the oiling port for those needle bearings. And this pin is pressed into the housing. And later on we have to take care of this hole here where a set screw is inserted. So let's keep that in mind. On the ram side we have to press out the drive pin. We have to be gentle here, of course, because it's cast iron after all. with precision surfaces, of course, but the press fit is not too bad. Don't go further. Yeah, fortunately that was the full length of the pin. So you see all the oil holes on the inside. We'll talk about this a little later in the video. On this ugly cover, we have to take off the table. Alfred Hitchcock would have needed some scenes like this in his suspense movies, for us machinists at least. And since I cannot look at this paint anymore, let's take it off with the most efficient and most cheap method available. That is using the flat scraper. Now, of course, that would not work on car bodies or any thin stuff, but on a thick cast pieces, best method ever. And I also did a slow motion in order to show you how that technique works. I challenge you to do this any faster with any other method. So here you can see it's a trade-off method where the angle of attack must be proper so that you have some thrust along the surface but also some force onto the surface, and then it works really nicely. And the rest is just repetition. The weapon of choice to clean up all the convex imperfections on the cast pieces is the hard roughing disc on the angle grinder. And I would not use the flapper disc for this because it's too soft, and the hard disc allows you to level imperfections in a very elegant fashion. And I rather take down convex imperfections than fill all the surrounding areas, which is nonsense and doesn't help with the resilience of the paint layer. All right, that's better. Now let's check, just visually, how far off the hole of the bearing pin is from the horizontal spindle. Since we all have it apart, now we can check it in a neat fashion here. Because we see that hole. And that's why I inserted that tool holder, because the tool holder gives us a reference. We see a gap in the bottom and none at the top. So how can that be? Well, to tell you the truth, at first I thought maybe there's a difference in design between the slotting head and my mill. Because the slotting head was made by the original designer of this mill, Wilhelm Grupp in Germany, which the tag says. And the serial number is 102, so also judging by the adjustability of the dovetail slide, I figured that this head is a later design. However, my mill was made after the design of the WF1 was sold to Switzerland, to Mikron, so maybe they changed the design after this step. So consequently, I measured the axis distance between the horizontal spindle and this hole here, which is the drive for the vertical milling attachment. And the measurement I get is 80 millimeters, quite exact. So I thought maybe the Wilhelm Grupp design didn't use 80 millimeters separation here, because the upper gear runs concentric with the upper hole and the lower gear should run concentric with the horizontal spindle. So then I thought, why don't I test the axis distance of those two gears and see if I get the same number. And tell you what, when I measured this, with the gears touching, I find a number of 79.95 millimeters. So clearly these two gears were designed and fabricated for 80 millimeters axis separation to give a healthy play between the gear flanks. So then I thought, obviously the hole in the housing of the slotting head is drilled in the wrong place. This head must have been sold at one point in time because it had a tag and a serial number. So if this was out of tolerance, it wouldn't have been sold. But how that could not have been detected, and also how they could not have detected that assembly error, I mean, this was not fatal, but how they could overlook this, I don't know. So what can we do about this? I guess we will rebore this hole to the proper location and sleeve it so that it still accepts the same axle pin. So maybe the guy who sold this head to me watches this video at one point in time, who knows? So the message goes to you, you trickster. You told me you ran this head on your mill, so... So there's no way around boring the hole into the proper location here. And for this purpose I have the housing clamped on the rotary table. Here I'm checking if the housing axis coincides with the rotary table axis. That's good. Next I place the machine axis to coincide with the housing axis. So essentially all three of those axes are now in the same location, roughly. And that's good. And let's zero out the DRO here. Now let's adjust the zero position of the rotary table. And to test this, I check on these two registering jaws on the housing that register with the machine when it's mounted. And I want the reading to be symmetrical. Then the rotary table is at 0, or the axis of symmetry of the housing is symmetrical with the machine. Here I'm centered in the old hole, just to check how far off it is. Alright, so we're centered here. And check the dimension, 80.6 almost, and it's supposed to be at 80. So we're now in the right place and have the Wohlhaupt boring head installed. It's a close call here at the housing. Yeah. Also we have to adjust the boring head, and it will be even closer later on. But let's give it a try at least. So spinning free. Let's touch off now in vertical direction. So that's our 0. Need a bit more speed. Let boring begin. And as you can already hear, it's an interrupted cut, and that's because the hole was so far off. My first cut is, I don't know, maybe half a millimeter deep. A bit less, I guess. I have to be very careful not to bottom out here, messing up my setup. That's good. You can see nicely that the cut is interrupted here. You can see where the old hole intersects with the new cut area. So we are not cleaned up yet. Let's adjust the next depth of cut. It's a very nice way to do it on the Wohlhaupter. And this is the final cut here. Let's take care not to mess it up. You see it's a very close call on the housing here. But it worked out, fortunately. I'm using the telescopic gauge to rough measure if we're spot on before we move away the boring head. But that looks good. Here I'm using a single point chamfering insert on the Wohlhaupter to chamfer that hole. But as you can see, something funny is going on here because the chamfer is not equal all the way around. So I'm thinking consequently the face of, and in this place here, is also not perpendicular to the boring axis. So let's remachine that face too. I'm just cleaning up the face so as to displace the gear axially not too much. But you can clearly see the surface was machined in a very bad fashion. It's not perpendicular to the housing face. And I'm cleaning up this surface until we have a proper flat spot. I have to use a long end mill here to reach this. So this is cleaned up now, almost. And since I'm machining the housing anyways, I thought I might as well also take care of the bottom surface. This surface collides with the coolant distributor on my machine. And also it doesn't really contribute to the rigidity of the slotting head. So I thought in order to reduce some strain on my body when I'm setting this up, I just might as well reduce some weight. So let's check if this brought an overall improvement. Installs nicely. Works out here at the coolant manifold. And the whole location now coincides with the horizontal spindle. It doesn't look like that from the video, it's hard to tell, but trust me. Here I'm machining some shallow pockets for the bolt heads, just to have a clearly defined edge for the paint layer to end at. Otherwise this would be no professional result. Here I'm blending the surfaces to give the part a nicely rounded look. Looks really retarded how I'm using the angle grinder here, but I'm left-handed and I want the sparks to fly into the barrel, so forgive me. And some hand blending of the radii just to match them. And that's the result. I think we can work with this. I also completely rescraped the slotting head. Here, for example, this is the first spotting cycle on the back surface. It's not plain. This is the front face. It's also not plain from the cutting pressure when it was manufactured. Here, completely rescraped. Sorry, I didn't take video here. Also the back side scraped. This is how I test for parallelism between the back face and the front face with the 2 micron per division indicator on my drilled spotting plate that I once made for the Mikron reconditioning. First spotting cycle on the ram, you can see the wear areas. Here after some scraping cycles, it was not too much wear, maybe 10 microns or so. First spotting cycle on the dovetail surface. All taken care of here. Now the slide surfaces on the swivel base, they were not too much worn, but they were tilted 40 microns. The upper corner here was high 40 microns and the lower one at 0. And this is how I tested for this, resting on some parallels on the surface plate. All taken care of now. It's a little hard to scrape with the oil pockets and get a decent surface finish, but worked out. This is spotting the dovetail weight piece against the ram, first cycle. So this is how I did that. Bluing up the ram. This is the last cycle. A critical step is checking parallelism between the dovetail surfaces on the ram. And I do this here by using the swivel base as a tool, sliding the ram back and forth and checking with the indicator. And then lastly, spotting the second weight piece against the ram. This is machining the sleeve for the drive pin out of 4140. That's a nice slip fit, just enough for the Loctite to get a bite on. I was planning not to press this, but rather to glue this, so as to keep the strain on the cast iron as low as possible, and taking the pressing loads of the pin just by the, or mostly by the 4140 piece. I think that's more elegant than having a press fit in the cast iron. Here I'm using this shim to feel how far to insert the bushing. And then after the glue sets, we need to drill the set screw hole through that sleeve. And I'm using a guide bushing here to not damage the threads, and then retapping the threads through the sleeves. And I also needed to modify this cover on top because of the access to the oiling port. Now I know you will say this is sacrilege. Alex, you're machining so much on these original pieces. Yeah, but you know, functionality comes first. So there's also a plaque that goes on top of this cover here in this particular location, but I figured when I make this slot here, the plaque is still readable and it doesn't look too stupid. You'll see later on. Here I'm interpolation milling some radii to give this a proper look. Yo. I also need to make that slot into the plaque. Alex, that's sacrilege! Oh, I don't feel that way. I feel it is an improvement. Chamfering the side of the cover with my trusty chamfering tool. I use it all the time. Here I'm roughing up the smooth surfaces on the housing to give the paint filler a better grip. I'm using the air engraver pen here. Sorry, I also didn't have time to capture video from the painting process, but this is the same as in one of my other dedicated videos, so I thought you can check up in these ones if you're interested. 2 cycles of fill priming and then painting. Here on the hot plate to bake the paint. That single coat acrylic came out all right, I guess. So let's start assembly. The adjustable stroke crank here and the retention pin works nicely. Now let's get on the new bearing. New bearing and the gear, and hopefully this time the right way around. Better check twice, Alex. There's a 50-50 chance. Okay. Snap ring goes in easier than it came out. Greasing up the secondary needle bearing. I'm not being cheap here because this is not accessible for lubrication from the outside. And making sure everything is properly greased so that things will slip together without a lot of friction for the given press fit it has. And now, watch out, Alex gets stupid. So here I'm thinking I'm being smart because I only want the forces, the press forces, to go through the ring and not through the bearing balls. Okay, so far so good. It has to go further down in the housing. Alright, let's take these bars and just push on the ring. Nice. But how to get the snap ring in? Tell you what, if the crank wasn't hardened, I would have completely machined it in order to allow for a more easy assembly. So obviously that bearing has to come out some distance again. And unfortunately there is no way around it. We have to apply pressure to the shaft to do this. And that means the press force is traveling over the bearing balls, potentially damaging the bearing that way. So I checked the press force during pressing, and it's roughly 1 ton required to move the bearing in axial direction in the hole. So how does that compare to the allowable load for this particular bearing type? I could only find numbers for the allowable radial loads, which is about 10 tons. So the axial load of 1 ton, 10% of that may be a fair number. I've checked the bearing by feeling it, turning by hand, and it felt all right. So crank has to come out even more in order to compress the locking ring. And now comes the tricky part, because we have to press the crank, at the same time compress the locking ring and feel that it will move into the bore. And I have to move the press with my foot because I need 2 hands to compress the ring. And once you go too far, you cannot compress the ring anymore because it gets pinched. So out with the bearing again. Back to the start. All right, let's try it again. So compressing the ring with both hands and moving the press with the foot, while not having a foot pedal. All right, out with it again. And one next try. Failure and out with it again. All right, let's try again. I should have bought these fancy ratcheting locking ring pliers. But you know, how many times do you need it? So finally. And now we have to press in the drive gear's bearing pin. But first let's grease up the needle bearings properly. Insert the drive gear and its shim on the back side. And now we have to align the hole in the pin with the set screw hole in the housing. And that's a bit tricky, so let's mark that first. And I'll try to align that mark in the press then. Yo. Aha! So with that new axle pin location, every tiny error on the gear flanks shows, and I felt two little hard spots over one revolution and decided to lap this error in the flanks away. And I drove the thing with just a bolt and a nut on it on the internal hex of the clamping screw. And it didn't take long for this process to work. It took me maybe 5 minutes to lap this in, so there was only a few microns interfering. Take a look at that. That's the way we want it. But of course now we have to get rid of all that grit, and that's why I didn't use diamond here but silicon carbide, because it's black and you can immediately see if there is something left. So here I'm flushing everything very thoroughly on the walls to make sure that no lapping compound is left. Oiling from the top and oiling on the needle bearings to flush everything out that may have found its way in there. And here you can see how some areas on the flanks got lapped. Only spots in the center of it. Also you can see we don't have that step anymore. Alright, let's check if everything fits and the drive works smoothly now. Here I have to align the drive dogs with the pegs on the horizontal spindle. Nice. So, seems to turn freely. These mounting bolts here are custom length, so I made those because those were missing, of course, when I bought the slotting head. And they also have a groove, which I'll show in a minute. Sounds well. So these grooves are for circlips, which have a retention feature so that the bolts don't get lost when you set up the head, or take it off rather. And those pockets in the housing, they are just for this purpose, that the bolt can move axially a certain distance but doesn't get lost. That's the way we want it. And here I'm mistakenly inserting the T-slot bolts before I put on the swivel base. Connecting rod is an easy assembly, but here I've taken out the T-slot bolts because I have to put on swivel base first, and now we can install the T-slot bolts. And some new nuts. Almost forgot the set screw that secures the axle pin. Next we have to press in the drive pin into the ram. And here you can see how the oil distribution works. So through the oiling port in the pin, into these holes and into the dovetail slides, and also out through the back to the connecting rod plain bearing, and through the connecting rod down to the other plain bearing. So let's be gentle here because we are resting on paint and we don't want to damage the cast iron. Nice, looks good. This is the locking screw for the pressed in pin. And here is a piece against which the tool rests when the axial forces of the tools travel into the ram. Assembly of the ram with the rest of the pieces is a bit tricky on this particular design because of the adjustment of the dovetail slide. So the left hand piece here, which I'm installing, that's the fixed dovetail piece. Alright. And these mounting screws on the face, they just tighten down. But the other piece is the adjustable one, and there's two adjustment screws, and when you tighten down the mounting bolts, that also tends to tighten the slide. So you have to adjust the adjustment screws and then back them off a certain distance, which you have to find, so that tightening of the clamping screws then gives a healthy play on the ram. And that's a bit going back and forth. Of course, we want to keep everything well oiled, the slide and the connecting rod, that is. Feel for the drag, but that's a little hard to tell. Later on, what proved more successful is to measure the play with the indicator. Yes, sir, it's officially moving up and down. The modification of this cover on top here, you can see how nicely accessible the oiling port is now over the whole travel. This pointer here shows the current adjustment of stroke, and the indication is right whenever the ram is in its lowest most position. So here we're at 80 millimeters travel, and I'm adjusting back to something, I don't know, 25 or so. And of course we don't want to forget the tag. Fortunately, I once bought a 2000 pack of those rivets. So here I'm adjusting the head swivel to be exactly perpendicular to the table surface with my precision right angle, because we have to renew this reference indicator here. This one is not well made in the first place, so I'm removing the old one and then making a new one. No, that's better. Then I made two different sizes of those tool holders for splining. So you see how the carbide piece is clamped here, and the carbide piece is ground on the D-bit grinder, and it's just a broken off piece of end mill. So quite simple. The relief in the back is just for a screw. Alright, so now let's see what we can do about those crank levers I mentioned in the beginning with the help of the rotary table and the slotting head. Shall we? So first we have to clamp the blanks in a fashion that its hole is concentric with the rotary table axis. That looks good here. I could have gotten away doing this without the parallel, but it helps with visibility. And here I'm finding the symmetry plane of the piece and adjusting the reference pointer on the rotary table and marking the worm crank position as a reference for the dividing work. So sorry, I have to feed with one hand, hold the lamp with another, look at the DRO, so the lamp is masking what we want to see here. But at least you can hear the cutting action. And what I'm doing here is to feed whenever the tool is free of the workpiece. Here a better view of the feeding work. So at 0 we begin to touch the bore, and I'm taking care to feed only when the ram is in the upper position. Feeding by feel on the hand wheel, but it's maybe 40 microns or so each cutting cycle. And we have to go to 0.7 something, I believe. And then the tooth is finished. So here hopefully we can see one tooth being formed or being shaped that way. Yeah, to the left here you can see the tooth taking shape. Here a better view of the rotary table. So once a tooth is finished we move free and then we unclamp the rotary table, do the next division, and off we go. So you see that doesn't really take long. This particular spline is one with missing teeth, in order to allow the crank to be assembled only in one position. And I'm test fitting the shaft here. There are still burrs in the splines. And also here the chamfer is missing, but I think you get the point. Can be assembled only in one position. So, but why splines then, you may ask? It's because of the strength requirement. A key would weaken the shaft too much in this case. So still needs to be slitted and drilled for the clamping screw, but I think you get the point. Play is good. And let's see what the customer says. And I couldn't live with me anymore if I didn't modify my vertical spindle storage holder to also accept the slotting head. And that's the way it works. Well, anyway, thanks a lot for your interest in this video, guys. I appreciate your time, and I hope you found the one or the other thing useful. And I'll see you on the next one. Bye!